Well, my name is Mark Lancaster, and I'm with Permian Production Equipment, and this is going to be a discussion about our new system for multi-phase compression, where that we can move not only gas as well as fluid, and doing it for horizontal wells. This is what our system is. Now, anybody over 60? Well, when I was growing up, this is how drilling an oil well took place. You know, all you had to do was poke a hole in the ground and oil came out. I mean, that's the way I learned it when I was in the 60s. You know, but the whole deal about this is all about pressure. Everything you do day in and day out in the oil field is all about pressure. Either you got too much of it or you don't have enough of it. So trying to get rid of it is what man has always been trying to do with oil wells. Now, you can do it in certain ways, like this operator, where he's actually venting the gas out of the wellhead to allow the pump action to go back to the pump. And he's doing it fairly safely. He's got a pipe, stand-up pipe, pushing it out a little ways, and you can see the gas go down. You know, but a lot of times oil wells have a mind of their own. And a lot of times they want to get rid of pressure when they want to get rid of pressure. And sometimes you have stuff like this happen. You know, because there's too much pressure in some part and it found a hole. And then sometimes this happens. You know, but everything we're going to talk about is all about pressure. Everything in any of these classes is all about pressure. And my boss was in the Monaghan sand dunes in the 1980s with a Gulf oil engineer, and they were looking at plunger lift at that time because that was a big thing for shallow wells was plunger lift. And they drove by a pumping unit, and the pumper had just blown down the well. And the pumper had done what that first guy did. He had run the piping back through the sand dune so it wouldn't be close to him when he blew it down because it had H2S in it. But unfortunately for this covey of quail, they happened to be running past at the same time he blew it down and killed the birds. And my boss at that time, and still to this day, is a big birder. I mean, and so from a conservation standpoint, he wanted to know, how can I blow down that well in an environmentally friendly way and not kill the quail? And that's how he came up with the beam compressor, which has been the main product we've had, because he saw that he had this big pumping unit that just goes up and down and hardly needs service, and it just operates and runs. He figured out that he could put in a cylinder inside of that structure, and he was taking a job. How many ever heard of Arm & Hammer? Arm & Hammer for decades had one product. And then all of a sudden somebody accidentally left it in the refrigerator, and now they had two products. And then that just emerged. Well, in the 80s, you could not find a brand new pumping unit, because there was an oil rush going on, and there weren't enough pumping units because Lufkin was pretty much the only choice. And so if you had a 640 pumping unit on a well that was making 5 or 6 barrels a day, and you just drilled a well over here that needed a pumping unit for 50 or 60 barrels a day, you were screwed. So what Charlie did was that he created a pneumatic lift system where he simply put a cylinder over the top of the wellhead, added a piston rod onto your rod string, and then he would stroke that rod pneumatically. That allowed the operator to take that 640 pumping unit and put it somewhere else. So he already had the basic idea that if he just took that pneumatic cylinder and put it inside the structure of the pumping unit, now the pumping unit can give him all the action as it's pulling this piston up and down. And these systems are in all over the world. This is a example of how we work. We're all about, once again, pressure. Bottom hole pressure is made up of what? Casing pressure and your hydrostatic head. So to lower bottom hole pressure, the simplest thing to do is get rid of the casing pressure. And so that's what we do with systems. So if you had a typical vertical or horizontal well, the main problem that you want is get as much fluid in your pump as possible. But what causes you problems? Gas pressure. Either the gas, because you have high casing pressure, the gas will go into the pump, or you get, it'll just be in the place where you don't want it to be, and it affects your operation. But if you go and get rid of that casing pressure by installing a beam gas compressor, you can drop your suction pressure and discharge into the flow line as you were before, but now you're giving the casing gas or the gas a different place to go because you've taken it off the well. Now the gas is going to go up the annulus, and as the gas goes up the annulus, now I don't think any of you have ever opened a beer. Because you're good guys. When you take that bottle of beer and you take the top off, instantly foam is created. As the gas bubbles go through the fluid, they create foam. But if you just let that bottle sit there, it'll continually see gas bubbles will go through the fluid, and it lets that fluid be less dense. Because if you just had the bottle with the cap on, the density of that fluid is much more than with the cap off. Same thing for an oil well. So if you're trying to lower bottom hole pressure by getting rid of casing pressure, you also create less dense fluid. Horizontal wells, most horizontal wells, you normally run them with 1,500, 2,000 feet of fluid over the pump because you can't pump it down because the gas goes in your pump. Unless you do something else, unless you go and get an Odessa separator or a heel system or a Predator or something to try to keep the gas from going in the pump. What we suggest is that let's get rid of the casing pressure first before you go and do something downhole, because I'm a whole lot cheaper to work on something on the surface. And a lot of people have like a Mother Hubbard already in the pump. If you have a Mother Hubbard that's already below your pump, and we take the casing pressure off, we're going to give you more fluid because we're going to give you a lower bottom hole pressure. Now, the only problem you run into is horizontal wells is, we did this for Oxy 5 years ago. We put 3 compressors on some wells they had in Carlsbad, and at that time they were running 90-foot tailpipes. All we did was make their gas interface worse. Because once we took the casing pressure off, the gas is wanting to move faster to the well, to the well bore, the vertical side. And when that pumping unit struck up, it just created a greater differential and maybe just sucked more gas up that tailpipe. Because I'm sure you all heard, gas, water's getting sucked up the tailpipe. Same thing as the gas when it goes up that way. And this is the reason. What we get into with gas and fluid is that, where's my pointer? Now I can use it. These are your gas bubbles when they're entrained in the fluid. They're small. But as soon as we lower the casing pressure above it, we're going to make those bubbles get larger and they're going to move at a faster velocity. Now, one of the big deals with horizontal wells used to be up in the Bakken was that they'd flump. They produce fluid up the backside. Well, I can take a well that's got 600 pounds of bottom hole pressure, and as soon as I take the casing pressure off of it, it's going to flump. Because even if it's 7,000, 8,000 foot deep, when I take that gas off there, I'm going to make gas, it's going to push that fluid to the surface, and it's going to come right up along the casing in the annulus. And my compressor doesn't really like that, because our beam gas compressors were designed to have relatively dry gas. We can have high BTU gas, but if you send me a slug of fluid, I'm not going to like that. But on a horizontal, you have a well that already has a tendency to foam. And it has a tendency to foam because you have this long corridor fluid and gas constantly going through it. It just keeps getting agitated. That's all that's going on. It's not really because the fluid wants to foam. It's just because you've got so much of it and gas rushing through it, it's going to foam. So when we take the casing pressure off, we're going to make that even worse unless we figured out how to stop that. So this is a well for EOG up in North Dakota. So they had a horizontal well making about 150 MCF of gas. And so what they did, they hooked the beam gas compressor to discharge the gas back in on this side. And this is the operator took this video, but he started backwards and started the back end. And then we get over, here's the line going up to the beam gas compressor. They're non-lubricated, so pretty much they just sit there and run. There's not a whole lot to mess with them on. And then you come down here, here's the suction side. That's my boss there standing in the way of the filming. And so here's the suction line where we suck the gas off of that line. But because it's a horizontal well and they had 750, 800 pounds of bottom hole pressure, we had them put a vessel over here on the side so it would capture any fluid that came up. Now the cost for us doing this is about $25,000, and then the vessel, they just have one out in their yard. So here, we can lower casing pressure very well on a horizontal well as long as we got some way to keep the fluid from when it comes to surface so we can stop it. But that gets to be problematic. And the reason why it sort of gets problematic is, Chevron has a steam flood that they operate out in Bakersfield. And about 6 years ago, now, is everybody familiar how a steam flood works? In a steam flood, they'll take, normally you got your wellhead and you got your flow line going off to here. Well, what they do is they engineer it so they can send 1,500 pounds of 500-degree steam back down the flow line so it goes down into the wellbore and hopefully goes out into the formation through the perforations in order to loosen up the fluid. And they'll let it sit there for about 3 days sometimes, and then they'll go and reverse the valves and take 1,400 pounds of that pressure back out because they can't get all of it back out. So they leave about 100 pounds down there. Now, oil in a steam flood is basically dead oil. There's no gas driving it anywhere. In a horizontal and a shale, you got all this gas drive going on. But in a steam flood, you don't have any of that. So that extra 100 pounds of casing pressure they added just doubled their bottom hole pressure. So what fluid they were getting was not nearly as much. So we wanted to put beam gas compressors on there, took the 90 pounds of casing pressure off, and we started making 40 and 50 more barrels of oil a day, which was great, which was wonderful. But in order to put that vessel between the wellhead and the compressor, Chevron's requirement was that they had to have a vessel that could handle 1,500 pounds of pressure and 500 pounds of steam, and they needed a pump that could take that fluid that gathered in that tank and put it back in the flow line. So I don't know if you've ever priced a 1/2 horsepower water pump that can handle 1,500 pounds of pressure and 500 degrees. It was twice as much as my compressor. So we're going, well, wait a minute, that's not, so they were spending $60,000, $80,000 for a system that was just really a Band-Aid on top of it. So what we started looking at, okay, now here you have a horizontal well. This has an Odessa separator in it. And this is, they've got casing pressure, they got flow line pressure, they got bottom hole pressure, their pump intake pressure. But as soon as we take that pressure off, we're going to make everything work better because we get more pumping pressure, but we also start slugging that well a little bit more. So what we designed was a hydraulic system to go on top of the wellhead instead of going on the pumping unit. And the hydraulic system, and you'll see here later, is really slick because we don't care if I get straight fluid, straight gas, or a mixture, because I can move it. And typically all I'm trying to do is move it from off the annulus and back into the wellhead so that this horizontal well can continue to produce. Now we talked about pressure. How many of you guys run ESPs? What's the worst thing in the world to happen with ESP? Casing pressure go from 100 pounds to 200 pounds, 100 pounds to 20 pounds. You know, they don't like that. Most wells don't. You know, and if you put a typical skid compressor on the surface on an ESP and you pull the backside on, you're going to do real well for a period of time until the scrubber tank fills up. And then that scrubber tank, once it fills up, it's going to do something. If it's through automation, it might have to pump all that fluid out, but more often than not, it shuts down. And when it shuts down, your casing pressure goes back up. So that's really not a good thing to your ESP or your downhole equipment. So what we started doing actually about 15 years ago was developing a method that we could drive our beam compressor that's been around for 40 years with a system that's been around for 100 years. This hydraulics has been around forever. This is your typical screw compressor, a piping and instrument drawing. This is what you normally get when you have a screw compressor. You got, you know, oil separator, a compressor, you got prime mover, you got temperature controls, you got a cooler, you got all this different other stuff. And the one thing that you don't see in here is the mechanic that comes along with this. You know, because the statistic I've always heard is that when you run these type of things, you need to have one mechanic for about every 6 or 7 units, because they're constantly having problems and fouling, and they normally run anywhere from 94 to 96% of the year. You know, for the last 6 years that we've been operating our system, we've been running at 99.9%. The only time we're ever down is when the automation messes up, more often than not. So this is the difference. These are all the different things that we don't have to have compared to our competitor. You know, and the thing I think the most about this is that we're very simple. You know, I like to consider myself simple-minded. You know, I mean, you know, simple is a whole lot easier. You know, with this type of system, you don't need one mechanic for every 6 units. You know, you can have one mechanic for hundreds, because the amount of problems you're going to have are yearly, not weekly or month by month. So this is what we're talking about. So we have a gas compressor that we have here on the bottom. And before, we took this piston rod and we hooked it up to the walking beam of the pumping unit. So as the pumping unit went up and down, we pulled our piston up and down. And we were not in control of which direction that piston was going, because the pumping unit was in control of it going up or down. Now we add a hydraulic cylinder here on the top, and we put a piston up there. Now we drive this hydraulically, and now we're in complete control of what we're doing with our system. So this is what allows us to be able to accept fluid. You know, because if I see gas and fluid comes into the bottom here and my piston's trying to go down, all of a sudden my system just reads that as hydraulic pressure. And we just push until we get whatever maximum number we want, and we just change direction. So we might short stroke for a period of time until we push all the fluid out. We might raise the casing pressure. Instead of it being at 5, it might go to 7 or 10 until we get all the fluid out. But we don't have to worry about it. One of the big applications for horizontal wells is, I don't think I've seen it too much in the Permian, allocation separators. You know, when you have 6, 7, 8, 10 well pads, normally the Railroad Commission likes to know how much each well is making. And so the solution has normally been, well, you take this big allocation separator and you set it on your big pad and you drive all your fluid into there so that you can measure everything going to that allocation separator. Then the allocation separator has to build pressure to send that fluid to a battery. Now, as soon as you build pressure in that allocation separator, what are you doing to all your well bores? You're building pressure. So by putting my system on the outside of that allocation separator, I can lower the pressure in the allocation separator to 15 pounds, whatever it takes to dump, and I can lower the pressure to all of the wells in the pad, and then I can compress the gas back in the flow line and use that to push back up to 200 or 250 pounds to push all the fluid to where you're trying to get it to. But with one simple thing, I can increase production on a large number of wells. So this is what happens, like how many are familiar with hydraulics? Hydraulics, you see it all the time on the garbage truck. You see all these devices that have these rams and stuff, and they just work. There's just not much to them. The heart of it is the directional valve, which is basically, is a valve that either goes this way or it goes this way. If it goes this way, it's sending fluid to the bottom of my device. If it goes this way, it's sending fluid to the top of my device. And so depending on which way it's going, that depends on which way this is going. So right now it's going up. And now it's going down. And that's the action of the system. There's really nothing else more complicated than what I've just shown you. It has 4 check valves. It has a pressure release valve on it. But one of the interesting things about it is, we're dual acting, just like our beam gas compressors were. We compress up and down. But if we get fluid in it, what happens? All we do is just keep on running. So we're sucking straight fluid. We've had customers buy them, like in Alaska, just to move fluid off of a rotoflex. It's not going to bother our system because we design it to run with the fluid. We don't need to scrub it out. We don't need to have dry fluid going into the compressor. None of that's worrisome to us. So typically our beam gas, our hydraulic compressors will have a suction side, and we'll put a pressure gauge, pressure transmitter on this side, and discharge, transmitter, temperature, and this is the guy that controls what we do. Because inside of the structure of the hydraulic system, we have a proportional valve, that directional valve I showed you. How much the valve goes left or right is dependent upon what kind of suction pressure, how fast do I want it to go. You guys are typically used to variable frequency drives, but most people don't like variable frequency drives because they're a pain in the ass. They're very persnickety. Well, here we can take a proportional valve, and depending upon whatever kind of programming you have, we tell that proportional valve, it's a 4 to 24 millivolt signal. Depending on how far you want it to be open, that tells the valve how much fluid it wants to send to the system. Sends more fluid, I go up and down faster. If I don't need to go that fast, it sends less fluid and I just go slower. But I don't require anything super special like a VFD in order to accomplish that. This is pretty much our standard system, where we'll have the directional valve that will be mounted here. We'll have a heat exchanger. We'll do fluid filters because we want to keep the fluid clean. We have a pump and we have a motor, and we have the compressor. That's it. The control system for this is whatever you want to put on. We do not provide you a control system because you already have people that are trained for that or used to that. We can use a Lufkin Sam's unit, or what do they call it nowadays? Well control, Allen Bradley, like anything that can give me 5 analog ports that I can plug a transmitter to, and I can tell a motor to come on. We've done it with Murphy switches. It's just to make it so it's really, really simple. This was one of our customers went and figured out how much they spent money on in the past 5 years. This is our hydraulic compressor. With this one was NACE compliant. So in the first year, the cost was you know, it was probably about $110,000, and some of that extra cost would be for their Allen Bradley and stuff that they put on there. Since then, they figured out that on their batteries, they normally already have a system that they can just add another card to the system they already have that's running all their other stuff, and we can piggyback on top of that. We don't have to have a separate system. But the thing they most enjoyed was this difference here, was the cost of service. You know, and this is mainly them allocating their own mechanics who just would drive by and say, oh, it's still running. So, you know, they still had to have a cost, but it was almost half of what our competitors are. You know, and maintenance on compressors equals lost production to an operator. The more maintenance a compressor, the less production. This is a typical P&I of our equipment. This is a fairly complicated system simply because we've got 3 pumps. We're driving over 300 MCF of gas from 0 ounces to 100 pounds of discharge pressure. You know, but that's pretty much as complicated as we get. You know, here's the motor and the pumps. Fluid goes over here. These are the proportional valves. Fluid goes here into this and tells how much fluid, and comes to our compressor and it comes back. You know, but if you looked at a P&I for a screw compressor for the same thing, I don't think you could see it on one page. I think it'd be multiple. You know, so there's a bunch of different advantages to our system. You know, I like no VFD. All of our systems are basically H2S compliant. You know, regardless of what you're looking at. You know, NACE compliance to us, we're really already there. There's nothing that we change to get to be NACE compliant. You know, there's not a whole lot, you know, because once again, you know, gas is going to come into our system. Everything's stainless steel already, 3,000 pounds. So there's nothing that we really have to change that's wetted by gas that has to be NACE. Whereas other compressors, they have a lot of components that they have to change out. You know, these are typical pressures. You know, like we can run them with a 10 horsepower motor, 20, 40, 75. We've got ones in the yard now at 150, 200 horsepower. We can do pretty much anything that you ever need. And what we're looking for is what kind of discharge pressure am I pushing into, and how low do you want me to go on the suction side in gas, and then I can tell you how big of a motor I need to have and how much fluid I need to drive. But, you know, it's a fairly simple concept. I said simple a couple of times. I like to. These are some different wells that we've got it on. These are, you know, it rained in New Mexico this day. It was last year, I guess, sometime. You know, but it's just a vapor recovery unit. You know, they just plumb it in. It just sort of sits there. Now this operator, this is the Allen Bradley panel that they have put on there, but now they don't put it on there anymore because when they were first doing this, they put it on the skid, and they had to have a Div 1 explosion-proof panel and stuff, and that was just ridiculous. You know, there's another one. This is one out here in Odessa. This is one out in Andrews. This was interesting because one of the things that happens with gas when you compress it is it gets hot. You know, and most skid compressors run at 3 to 4 ratios of compression. And the reason why they run at 3 to 4 ratios of compression is because if they ran faster than that, they'd get too hot. Well, we run at 9 ratios of compression. Hot is not an issue to us because, okay, how many people are married? Brave people. Now, my system runs at 5 to 9 cycles a minute. A skid compressor runs at 1,500 cycles a minute. You know, and you know, and you got something that's going back and forth that fast, it's going to get hot. With my system, every time I stroke up, I'm drawing cooler gas into the cylinder. Then when I push down, I heat up the cylinder for a split second, but then I'm pulling cool gas back into it. And because there's large volumes of gas, and because I'm running at 9 cycles as opposed to 1500, I don't have the problem with heating the gas up. So what happens when you heat up gas in West Texas? As soon as it hits the sales line, it cools off. And as soon as it cools off, if it's got any BTU in there, it's going to form condensate. Now you're pushing condensate to your gas plant, and they sort of don't like that. So with our compressor, we can sit in a situation, because we're not going to heat up the gas, we're not going to allow the BTUs to drop out. And so we just push the gas down, and we don't have any issues with that. You know, and so that's not bad. This is a system that we have in North Dakota. And what I really like about it, this is a junction panel they had going to their Allen Bradley over here. We shipped this up, and none of my people went up there to look at it. I gave them a little installation manual, about 7 pages. They saw the 5 places that they had to hook their transmitters to. They turned on their Allen Bradley, and it worked. You know, and it's been working, I guess, when did we put it in? 2015, so it's still operational. And they have yet to pick up the phone and say, Mark, it broke. You know, because there's just nothing to break. You know, there's just not that much in. This is one of our larger systems where we have a 150 horsepower motor. This is a triple vane pump. And this compressor is 100 inches tall, which makes this 100 inches tall, which means this whole thing is real tall. You know, but real tall is okay on most oil pads. Tall is not that big of a deal. And we put it in multiple pans as far as depending on how much fluid we're going to have, so we have a capacity to hold fluid if in the worst case scenario we get a leak. This is the well I was talking about that we do for Chevron. This is out in Bakersfield, and they put a unit here so that they can take gas off of 5 different wells as they, you know, steamed them up. You know, many of you have heard the term blow-by. You know, on a skid compressor, blow-by is a big deal with the EPA. You know, because if you have that piston pushing and compressing gas, you'll have gas will seep around that piston seal and go out to atmosphere. You know, it's just going to happen. You're not going to be able to do all. So a lot of compressor systems, they'll put a different exhaust thing on here so they can capture that and resend it in if they're a gas fire, so they can reburn it, or they got to do a lot of extra stuff for that. I don't worry about it. And the reason why I don't worry about it is that we have a triple redundant seal in our middle head. So this is where our middle head is. Now, the hydraulic cylinder runs at 700 to 1400 pounds of pressure. So it's pushing down pretty hard. The gas side will barely ever get over 400. So our seal is constantly closed. So gas can't escape this way. So from the point where the gas comes in and the gas leaves, there's really nowhere for the gas to ever escape our compressor. You know, if the EPA came by with one of their FLIR cameras, they're not going to see any gas escaping from my stuff. Your stuff, I'm not going to say nothing about. But my stuff, I'm not worried about. You know, so we got it on service. Now this is the deal in California where they had multiple wells they were steaming, and they hooked up multiple units so that they can go ahead and pull it off of multiple wells. Actually, in some places, you know, some of the steam floods, they'll steam them for a longer period of time. They just go and mount them on a trailer so they can just haul it around. Because once they pull that 100 pounds of pressure off the well, it's not going to get any more pressure because it's dead oil. You know, so it doesn't have to sit there full time. It just needs to be there long enough just to pull the pressure off after they've released the gas. ESPs, you know, I think on an ESP, this system is remarkably well. You know, we've done a few, but most of them have been in the Middle East. You know, because and in the example in the Middle East, how many of you ever designed an ESP? You know, don't you design it for gas interference? Why? Because you don't have a way to get rid of the gas. So if I have a way to get rid of the casing pressure in the annulus, the odds are the gas interference in your ESP is going to be considerably less. If I have less casing pressure, I'm going to have lower bottom hole pressure, you know, so it's going to make your ESP run more efficiently, you know, and so it's just going to allow you to have greater pump fillage on that ESP with less hertz to be able to do the same work. And if an ESP uses less hertz, I would think it works for a little while longer. In Mississippi, we did this one time where the guy had all of his wells were run on propane. So they had a central place where they pumped all the propane to those locations, but the problem was in the winter, those propane lines would get cold and the propane would drop a lot of fluid out, and then the fluid would freeze. They just run into a lot of problems. So here, because I can run with wet or dry, I can push everything and we could keep it constantly running. Talk about that. It's an interesting system, you know. We had in Colombia, we do all the work for Ecopetrol, and they were looking at setting a really large compressor for $4.5 million to move a million cubic feet of gas a day. Maybe that's the wrong number. But we just went and put 20 of our units in there. We just manifold them together. You know, our cost was a third of what the one compressor was. You know, but then we also told them and showed them, because we had an extra system in our 20, because we only had 19 run at any time, that if any of them needed to be serviced, well, we just turn on that 20th one. So now instead of having 99.9% runtime with our system, they've got 100% runtime because they've got a constant backup. Whereas with the other one, when their one big compressor went down, they would lose a lot of production. And obviously it's going to go down because you got to maintain it, you know, not to say whether it just actually breaks, you know.